Greetings, everyone. This is your review PowerPoint for Unit 2, Atomic Theory. I'm going to go through the unit and hit the high points and try and help you make sense of the material in this unit, sort of to help you bring it all together so that you go into the test feeling comfortable and confident. That is my goal, and throughout this we'll do a few examples, and I'll mention the most important things to keep in mind. So Democritus, really the only thing to know about him is that he is the origin of this word atom, the idea of the atom being indivisible. Now we know now that the atom is divisible. Many of them are in nuclear reactions, but we didn't know that at the time that we were coming up with the name atom. And so we simply refer back to Democritus for this idea that he gave us of the atom. The law of constant composition is pretty straightforward. You can understand what it's saying just based on its title. But it's basically telling us that a given compound always has the same percentage of each particular type of element. Again, that's obvious to us today, perhaps. Back in the day, it was not obvious because they didn't have a strong understanding of the difference between mixtures and pure substances. But this law holds true pretty well. There are a couple loopholes involving some very exotic substances, which we will not talk about. But John Dalton, of course, was contributed the atomic theory of matter, which consists of 4 postulates. Now, I would strongly urge you not to memorize these. I don't think that would be a good use of your time. However, I would urge you to read through them carefully and make sure that you understand what each is saying. So basically, the heart of the theory, and remember, a theory is an explanation for patterns that we see in nature. The heart of this theory is that matter consists of atoms, and that can explain a lot of the laws that we had at the time. John Dalton says all atoms of a given element are identical but differ from those of any other element. Remember, that is not entirely true because of isotopes, which of course they didn't know about back then. But atoms of a given element are quite similar, and they just might differ in terms of the number of neutrons. Atoms are neither created nor destroyed in any chemical process. Note the word chemical there because there is an exception to this in which atoms can be created or destroyed in a nuclear process, but not in a chemical process. And this point is basically providing an explanation for the law of conservation of matter. And finally, a given compound always has the same number and relative types of atoms. Well, this would explain the law of constant composition, which we saw before. If matter consists of atoms that are always the same, then it would make sense why the percentage by mass is always going to be the same. All right, J.G. Thomson is really the first experiment in which we really begin to understand what's inside the atom. We have strong evidence that the atom exists, but we don't really know much about it at this time. So basically, John Dalton used a cathode ray tube, and the cathode ray, he discovered, was really just a stream of particles. And after applying a voltage source to 2 metal plates, and this worked for pretty much any metal, he found that when he put it in a magnetic and an electrical field, we'll talk about the electrical version because it's much easier to understand. When he put it in an electric field, he found that the beam bent upward towards the positive plate. He deduced from this that this stream of particles must be negatively charged. Essentially, Thomson discovered the electron. But he also knew that matter was neutral, and so he knew there must also be positive charges in the atom. But at the time, of course, they didn't know how they were distributed. So sort of from Thomson's work, we come up with the idea of the plum pudding model, in which everything's just kind of thrown in there together in no particular order. And it took Ernest Rutherford and his famous gold foil experiment to disprove the plum pudding model. Rutherford was shooting alpha particles, which they knew at the time were positively charged particles. He was shooting those at a very thin sheet of gold foil. expecting that the vast majority would pass through, really expecting that all would pass through. And in fact, the vast majority did pass through. But what surprised Rutherford was that several of the alpha particles were deflected at very large angles. And he concluded from this that the atom must be mostly empty space, but that the positive charges are concentrated in a core in the atom's center, and only that concentrated core of positive charge would be powerful enough to deflect these incoming alpha particles. So here's just a look of what on the left, what the experiment would have been like had Thomson's model been correct, and then on the right here, the actual results. And so after these experiments, by the beginning of the 20th century, we were aware of 3 subatomic particles, the proton, the neutron, and the electron. We know that the proton and the neutron have a mass of approximately 1 atomic mass unit. Now, their mass in terms of grams or kilograms is exceedingly small, which is why we developed a new unit to actually measure the mass of an individual atom. And we see here the mass of the electron is only a tiny, tiny fraction of the mass of a proton or neutron. And that's why we essentially say the mass of an electron is 0 or negligible, because it's so small. Obviously, the proton is positively charged, the electron is negatively charged, the neutron does not have a charge. And of course, we know now where these particles are. It's important that you understand what this symbolism means and how to write a particular atom using this notation. So Z is the atomic number, which is the number of protons. Remember, we can get that on the periodic table. A is the mass number, right, which is achieved by adding protons plus neutrons. Please don't confuse that with atomic mass, which is the average of all of the isotopes. And remember, we find the atomic mass on the periodic table. We do not find the mass number on the periodic table. If the species is charged, that means there's an imbalance between protons and electrons. If it's positively charged, there are more protons, and if it's negatively charged, there are more electrons. If it's neutral, it means the number of electrons is equal to the number of protons. So it's very important that you can, if given protons, neutrons, and electrons, come up with this symbol, or if given the symbol, come up with protons, neutrons, and electrons. And the element puzzle is a great tool for testing your ability to do that. Isotopes are elements that are identical in terms of the number of protons, but have a different number of neutrons, and this manifests itself in terms of the mass number. And here we define atomic mass, the average of all the isotopes in existence. You can look at the atomic mass on the periodic table and get an inkling of the relative abundance of particular isotopes. For example, the atomic mass of carbon is 12.01. Now, from that information, given that the average is almost exactly 12, I would deduce that the vast, vast majority of carbon atoms have 6 neutrons in the nucleus. And in fact, that deduction would be quite correct. As you see here, approximately 99% of all carbon is carbon-12. And a tiny percent, 1%, is carbon-13. And an even smaller percentage, which they don't have listed here, is carbon-14. And carbon-14, incidentally, is pretty important in terms of radiocarbon dating because it decays at a predictable and constant rate. And because these don't differ chemically in any really measurable way, these carbon-14 atoms are just kind of randomly distributed through all matter. And so once something dies, essentially the interchange between the organism and the environment ceases, and the clock starts ticking, in a sense, in terms of the decay of carbon-14. And so we can measure the amount of carbon-14 remaining and determine the age of something. It's really quite a useful technique, and it can be quite accurate as well in terms of getting the age. This term isoelectronic means two different species that have the same number of electrons. So obviously, one thing I want you to see right away is if two things are isoelectronic, at least one of them has to be an ion. Remember, an ion is simply an atom with a charge. And there's just no other way to get two species to be isoelectronic, because if they're two neutral elements, they're going to have a different number of protons, and hence they're going to have a different number of electrons. So to make electrons equal, we have to create an ion. All right, before I move on to the electromagnetic spectrum, I just want to make you aware of something that's really important for this test, and that's going to be understanding the various historical models of the atom. And there's a good question on this on your review sheet problems, pretty much the last question, which asks you to draw the model of the atom at various points in time. So for example, if we were going to draw Democritus's model of the atom, we'd simply draw, billiard balls. If we were going to draw Thomson's model, we'd draw the plum pudding model. If we were going to draw Rutherford's model, we'd show a nucleus with electrons in the cloud outside. If we were to draw Bohr's model, we would have a nucleus as well, but we would have electrons orbiting the nucleus. And if we were to draw the quantum mechanical model, we would again have the nucleus, and we would have the electrons in orbitals swirling around the nucleus. So, for example, if I were to, ask you, well, which of these models does the atom contain a nucleus, right? Well, that's going to be obviously the quantum mechanical model, the Rutherford model, the Bohr model, but not the Thomson model and not Democritus's model. So make sure you have a good understanding of the various models of the atom from a historical perspective. Okay, moving on to the electromagnetic spectrum. You do need to know this, and in class we talked about some mnemonics, including Roy G. Biv backwards, knowing that infrared light is right next to the red light, and ultraviolet is right next to the violet. X-rays and gamma rays are quite harmful. Gamma is more harmful. And then, of course, radio waves are on the far end, and that leaves microwaves right here. You need to know the relationship between frequency, energy, and wavelength. You do not need to know the equations, but you need to know, for example, as energy goes up, frequency goes up. As frequency goes up, wavelength drops. And as wavelength gets smaller, the energy gets higher, right? So we have a couple of inverse relationships and one that's direct. And now we can begin our journey into quantum theory. And the main point about quantum theory comes from this word here. And that's the idea that electrons are quantized, that they are only permitted to have particular energies. And so here are the main points of the Bohr model. One, electrons are quantized. Two, electrons exist in discrete orbits. So remember, Bohr thought that the electron orbited the nucleus. Finally, electrons absorb energy. When they get excited, they move to outer energy levels, and then when they get pulled back towards the nucleus by the protons, they release energy, and some of that energy we can see in the form of light. So to first just analyze Bohr's points here, one of his biggest contributions was that electrons were quantized, and he envisioned them being quantized because they were orbiting and they were only allowed on particular orbits. Today we know that Bohr was incorrect about the orbits. We'll talk about that in a second. But he was correct, as far as we know, about electrons being quantized. We have a lot of evidence for that, most importantly, the line spectra. So this point here is incorrect. This third point is still accepted today. As long as we don't think of the energy levels as orbits, this is still accepted today. And that when we put energy into the atom, the electrons move to outer energy levels, then they relax, and they give off energy. So two important points here to see this line spectrum, these very specific colors of lines. we need to do two things. First, we need to excite the element somehow. And that typically involves either putting it in a flame, like you did in the flame test lab, or having one of these gas tubes and putting a number of volts of electricity through it. That also works. The second thing we need to do is we need to look through a prism, because if we don't look through a prism, all of these colors that are produced are going to meld together and appear as one color. So we can separate them out by looking through that prism. And when we do that with hydrogen, we see this very famous and distinctive line spectrum with 4 colors. And we actually have the ability, and there's a very sleek equation as well, to calculate these energies. Because we know exactly which transitions in the hydrogen atom produce these particular lines. So the 3 to 2 transition produces the red line, 4 to 2 green, 5 to 2 is the blue, and 6 to 2 is the violet. These are the only visible colors that we can see. That's a little bit redundant, isn't it? If they're visible, we can see them. There are many other transitions, however, which are occurring but are not transitions that we can see. So you see the 4 colors there, those transitions back to n equals 2. But we also have other transitions in the hydrogen atom that are outside the visible range. And as we discussed in class, these transitions here from all of these levels down to n equals 1, these are releasing ultraviolet light. And these smaller energy transitions, going back to n equals 3, going back to n equals 4, this typically is infrared light up here, right? Now, one thing to be able to explain is the reason that these energy levels converge, right? Now they're getting closer and closer together, and shortly above 7 is n equals infinity, at which point the electron has essentially left the atom. So why do the energy levels get closer and closer together? Well, it has to do with the fact that it's difficult to move the electron from n equals 1 to n equals 2. That takes a lot of energy because you're very close to the nucleus. But then to go from 2 to 3 and subsequently from 3 to 4, that takes less and less energy because you're getting farther and farther from the nucleus. And so that's reflected in the fact that these energy levels converge. And the convergence of these energy levels also, of course, helps explain why we see a convergence of lines in the hydrogen line spectrum. Now, as we know, these line spectra are fingerprints, and so they're extremely useful to us. We can use them to identify elements in a particular sample. However, moving on from Bohr realized pretty soon after he had shared his work that his calculations, his equations only worked for a single element, hydrogen, or another element that's hydrogen-like in the sense that it has only 1 electron. So his equations would work, for example, for He+, which only has 1 electron. But you add another electron in there, and the equations don't work at all. They don't come close to predicting the observed energies. The other problem with Bohr's model, which we talked about in class, was that if in fact Bohr was correct that the electron orbited the nucleus like the planet orbited the sun, then this accelerating charge should radiate energy. And if it radiates energy, then it would eventually slow down. And if it were to slow down, it would eventually spiral into the nucleus and collapse in the nucleus. Now, we know that doesn't happen. And so logically, we must therefore conclude either we're wrong about the fact that an orbiting charge should give off energy, and we have a lot of evidence to suggest that is correct, or the electron is in fact not orbiting the nucleus. Now, there were some subsequent discoveries that lead us to our modern understanding of the atom. And one important discovery was that electrons, like light, can behave both as particles and waves. And it's these wave-like properties that really lead us into the new quantum mechanical model of the atom. The whereas Mr. Carr analogy helps us understand the Heisenberg uncertainty principle. That is, just like sending a tornado into the school to find Mr. Carr, if we want to look for an electron, we have to send in some type of radiation that will bounce back and tell us where the electron is. The problem with that is once the radiation hits the electron, it will knock it off its path because the electron is very small, very light. And so the consequence is that we will never be able to determine both the location and the momentum of an electron. We can know one, but not the other. The more we know about one, the less we know about the other. And so this leads us into our modern model of the atom, in which electrons are still quantized. So this is an important similarity with Bohr's model, is that electrons are still quantized. 2, electrons have wave-like properties. It's a contribution of Louis de Broglie. And 3, the Heisenberg uncertainty principle. So we need to somehow develop a model of the atom that incorporates all of these points. This diagram on the right helps us understand how the electron is quantized. So again, Bohr was correct that the electron is quantized. He was incorrect about how it was quantized. He thought that it was quantized because it existed on a specific orbit. But our understanding now is that the electron is a wave, and it's quantized because if you have a wave that's fixed at 2 points, and we can envision the electron being kind of bound in the atom in the same way, then only specific vibrational frequencies are allowed. Any other frequencies, the wave destroys itself and essentially can't exist. And we saw this in class as a dramatic demonstration. So in the quantum mechanical model, the idea is, again, n equals 4 is okay, n equals 5 is okay, n equals 4 1/3 is not okay. Under those conditions, the wave would destroy itself. So we've gone to look for the electron many times, and we find that it tends to hang out near the nucleus. It doesn't appear to be in any kind of circular orbit. And we have found the electron in different patterns. Okay, so one pattern is a spherical pattern, and this is called an s orbital. And remember, there's always a number that goes before the orbital, and that's the energy level. As we go from 1s to 2s to 3s, we see the size of the orbital increases, and the reason is that the electron with more energy can spend more and more time farther from the nucleus, right? And remember, we define an orbital as a region of space where we will find the electron 90% of the time. Now remember, an orbit, an orbital, is very different from an orbit, 2 totally different things. An orbit is a path that the electron follows around the nucleus, whereas an orbital is a large region of space where we have a good chance of finding the electron. So make sure you can differentiate those. You do need to know that there are 3 p orbitals, and you do need to know the shape of the p orbitals. As we go beyond p, you do not need to know the shape. However, you obviously need to know there are 5 d orbitals and 7 f orbitals. Again, all these things are regions of space where we're likely to find the electron. One question that sometimes comes up is, with all these orbitals, why do atoms seem somewhat spherical in the way they behave? And the reason is all of these orbitals are piled in on top of each other. And so you can imagine all these little orbitals. This helps us understand what this looks like. But if you were to kind of trace a line around all of it, a 3-dimensional boundary, it does appear somewhat spherical. And these electrons, of course, swirling in these different shaped orbitals. But if you were to look at the electron from 10,000 feet, which of course you wouldn't be able to look at the atom from 10,000 feet, which couldn't be done, obviously, because it's so far away. But if you were to take a bird's eye view of the atom, you would just see a bunch of sort of electrons swirling in a circular cloud. As we put the electrons in the atom, we have to follow 3 rules. The first is the Aufbau principle, which tells us electrons fill lowest energy to highest energy. All right, so to keep track of the order, we have to follow the periodic table. You're not going to get this chart, so you need to understand, where these come from. And I guess the way to remember it, I think, is to remember the S block is over here. It only has 2 elements that make it up. The P block has 6 elements that make it up. It's over here. The D is 10 and the F is 14. Obviously, these numbers are not random. They come from the fact that there's just one type of s orbital, and each orbital holds 2 electrons. 3 types of p orbitals, each holding 2. 2 times 3 is 6. 5 d orbitals times 2 is 10, and 7 f orbitals times 2 is 14. That's where that comes from. Do remember, when you go from s to d, you drop 1. When you go from s to f, you drop 2. Pauli exclusion principle says that when you put 2 electrons in the same orbital, they must be spinning in opposite directions. And finally, Hund's rule, which says that within a particular sublevel, that is 3 orbitals or more that are all at the same energy, the rule says you must first put in the electrons so that you maximize the number of unpaired electrons, and then pair only when absolutely necessary. And the reason for this is pretty intuitive, which is that if electrons are negatively charged, then being in the same space as another electron is going to cause repulsion. And if there's an empty space in a nearby orbital, that electron, this electron here, is simply going to be kicked into that next orbital. And that's why this rule is true. So make sure you can identify the various pieces of the electron configuration: the energy level, the orbital, and the number of electrons in the orbital. And remember, the orbital diagram consists of an arrow and either a box or a line. I like to do the lines, in fact. So to abbreviate, this can be a very useful way to write an electron configuration because it can be quite long to write out all the terms. And as we saw in class, germanium is the examples. But like any, but all the examples work the same way, and that your first step is to go back to the first noble gas and then work your way forward from that noble gas to the element. So make sure you put the noble gas in brackets. Then, of course, here we have 4s2. We remember to drop 1 when we go into the Ds, 3d10, and then back to 4p2, right? And that is the abbreviated configuration, which is really much more convenient. So we also learned in class the term paramagnetic and diamagnetic. It's paramagnetic if it has unpaired electrons. And what that means is these unpaired electrons are spinning in the same direction. This creates a magnetic field, which will interact with an external magnetic field. Now you have some elements that are actually called ferromagnets, which are supermagnetic and can act as magnets themselves. The classic example is, of course, iron. And if you were to do the electron configuration, the orbital diagram for iron, you would see that it contains a very high number of unpaired electrons. The opposite of paramagnetic is diamagnetic, right? These things do not interact with a magnetic field because all of the magnetic fields that are created by the spinning electrons are canceled by the electrons that are spinning in the opposite direction. How do you do electron configurations for ions? For example, if we're going to go from Na to Na+, you're just going to take an electron away. Remember, always take away the outermost electron. So we can say that Na+'s electron configuration is simply Ne in brackets. That's perfectly acceptable. Calcium, if it forms calcium 2+, again, you're going to remove those outer 2 electrons, and the electron configuration is simply argon in brackets. And aluminum, if we form aluminum 3+, again, take away, in this case, you have to take away first the 3p electrons, then go and take away the remaining 2 electrons in the third energy level. If we form a negative ion, okay, you're just going to add an electron on. So whereas hydrogen is 1s1, H-, which is isoelectronic to helium, would simply be helium in brackets. If we go from F to F-, we can simply add an electron on, or we can write neon in brackets to abbreviate. And oxygen, if it forms 2- charge, again, just add the electrons on. And that happens to be, I hope you're seeing this, that these 2 are isoelectronic. Oh, forgot about nitrogen. Same deal with nitrogen. Third species here that happens to be isoelectronic with those middle 2. All right, what gets tricky is when we try to do electron configurations of ions of transition metals. And the rule of thumb to remember here is that electrons are always removed first from the valence shell. And the tricky thing about transition metals, which are those elements in the middle of the periodic table, is they put a couple of electrons in the valence shell, but they're filling the d orbitals, which are deeper in the atom. They're actually not valence electrons. So, for example, this is the electron configuration for iron, right? If we were to form a very common ion of iron, Fe2+, your instinct might be to take away these two electrons here and write 4s2 3d4. You have to fight your instinct on this because the outermost energy level here is not 3, it's actually 4. So you have to take these 4s electrons away when you form Fe2+. So the electron configuration is simply argon 3d6. Now if we were to take another electron away and go to Fe3+, that's when you then have to dig into the d orbitals and take that last electron away. So the electron configuration here, argon 3d5. Here's just another example, manganese in its neutral state. And then if we take a couple of electrons away, again, remember, take them away from the 4s, we get argon 3d5. The color of transition metal compounds, right? We talked about this just briefly in class. These transition metal compounds can make some really beautiful colors. How do they do it? Well, they do it by having unpaired electrons in the d orbitals. And the d orbitals differ in energy in such a way that that energy happens to correspond with visible light. So basically, electrons can be promoted from one set of d orbitals to the other set, and that absorbs a particular color. We, of course, see the complementary color to that. But in order for this to happen, there has to be unpaired electrons in the d orbitals, right? If you don't have any unpaired electrons, well, if you don't have any electrons in the d orbitals, and this would be an example like scandium 3+, which is a transition metal but has no electrons in the d orbitals, then that's not going to show a color. On the other hand, if you have all of the d orbitals filled with electrons, as is the case with, for example, Zn2+, then you're also not going to see a color. But if you do have unpaired electrons in the d orbitals, the compound is likely going to be colored. So, for example, Cu2+, which I believe the electron configuration, I don't have it here, but I believe it is argon 3d9, or is it argon 3d8? I think it's argon 3d9, just going off my memory here. But in any event, there are unpaired electrons in the d orbitals, and so that's going to be colored, whereas Zn2+, which has an additional electron, has all the d orbitals filled, and so that is colorless. I also just want to make sure you understand what an excited electron configuration looks like. So, for example, carbon, we have two different states that carbon could be in. One is called the ground state. That's always the lowest energy state. And so to get the ground state electron configuration, you're just going to follow your rules that will tell you what the electron configuration is. Now, if I put carbon in the flame, or I put electricity through it, these electrons are going to move away from their ground state configurations. So there is literally an infinite number of possible excited states. Okay, here's just one possible excited state. What you can see is the electrons are completely out of order in terms of the order of filling, and that's the way it is because the electrons have been pushed up to higher energy levels than they would naturally be at. So, for example, if you were to see an excited state electron configuration, how would you know what element it is? Well, the best way to do that is to simply count the total number of electrons. So if I saw this excited state, I would count 4, 5, 6 electrons, and I'd have to know if it's neutral. If it is neutral, then I'd know, well, this is an excited state for carbon, right? When the electrons are excited, you might get some situations in which Hund's rule is violated because, again, the electrons could be pushed together where they wouldn't naturally be together. So, for example, normally when we look at 2p3, we would expect we'd have one electron in each orbital. Well, in this particular case, if it's excited, that may not be true. However, if you're told it's true, then obviously follow Hund's rule. The one rule that cannot be broken, it seems, is the Pauli exclusion principle. So if two electrons are even just temporarily in the same orbital, they have to be spinning in opposite directions. That is the rule. So that concludes our little review, and I think I've hit all the major points here. Again, look at the bullet points on your review sheet. How do you review for this? You go through your notes, you go through the PowerPoint, you do some of the old practice problems. Make sure, again, that you know this at a level which is deeper than simply memorizing what's on the PowerPoint, but that you could explain these concepts to someone else, someone who has not been here for this unit, and so that you could dig deep, because the questions are going to be trying to get at whether you have a deep understanding of these concepts and principles, and that you can apply what you've learned to new examples and problems. All right, everyone, this concludes your review. I look forward to seeing you in class, and I look forward to seeing great success from all of you on this test.